Hello and welcome to my channel. Today's topic is an introduction to biochemistry. So we will be going over all of the concepts and ideas that you will need to know for biochemistry. Okay, so for starters, we're going to start off with a bit of simple recap, maybe review type stuff. Anyway, so biology is the study of living things, and then chemistry would be the study of matter. So therefore, in simple terms, biochemistry is essentially the study of living matter. All matter, which is anything that has mass, is made up of elements, which are made up of atoms. You've probably all heard the joke, why can't you trust an atom? Because they make up everything. Anyway, might sound corny, but it is true. Everything is made up of atoms. Atoms contain a nucleus with positively charged protons and neutrally charged neutrons. Protons determine the atomic number of an element. For example, oxygen has 8 protons and is number 8 on the periodic table. The atomic mass, on the other hand, is the amount of neutrons and protons in the atom. As we already talked about, oxygen has 8 protons. And it also has 8 neutrons, which gives it a mass of 16.0 AMU, or atomic mass units. Which, if you didn't know what that is, it's 1/12 the mass of carbon. But, so we know that oxygen has 8 and 8. What about lithium, which has a mass of 6.94? What does that mean? Does that mean we only have a 94th of a proton or a neutron? No. This is due to isotopes. Isotopes are atoms that only differ in the number of neutrons. And in the case of isotopes, forming is included in the mass. By forming, I just mean the chance of that isotope forming, because not all elements are going to form an isotope. It's not, lithium isn't always going to form an isotope, but since obviously it has 0.94, that means the chance of it forming an isotope are a lot higher than other ones. For example, hydrogen has a mass of 1.01, which means there is 1% chance of an isotope forming. This would be hydrogen 2, which means there is 2 neutrons and 1 proton. The nucleus of the atom is also surrounded by negatively charged electrons, which move around in what we call orbitals. The mass of an electron is very, very small, which is why it doesn't have an impact on the overall mass of an atom, as it only weighs roughly 9.11 times 10 to the negative 31 kilograms, which is quite small. Scientists cannot determine the exact location of electrons. We can only really determine where they're most likely to be, which we call these clouds of electrons, because we don't know the exact location, but for example, in this certain area, we can know there's greater chance of electrons being here than in another area. Valence electrons are the electrons in the outermost orbital or shell of the electrons. So there can be multiple shells in different elements. So for starters, our first shell can only contain 2 electrons, and then your second shell can contain 8, and so on. Valence electrons is what is involved in bonding 2 or more elements or molecules. So there are 2 main types of bonds. We have ionic bonds and molecular or covalent bonds. An ionic bond forms when a metal and a nonmetal transfer their valence electrons between each other, and the result is either a positively charged cation or negatively charged anion. And they are called ions because they have a charge rather than any element is in like its ground state, so it doesn't have a charge on it, whereas ions do. And then if the element were to gain electrons into its valence shell, then it will have a negative charge, whereas if it were to lose electrons, it would have a positive charge. For example, when we look at sodium chloride or table salt, sodium has 1 valence electron, whereas chlorine has 7. And since they both want a full shell, then sodium will donate its extra valence electron to chlorine so they can both have a full valence shell and be stable. And then so ionic bonds are bonds that have an electronegativity difference of greater than 1.7, which is the electronegativity of 1 minus the other, but it's an absolute value. So it doesn't matter if you subtract or add because we don't count the negative. And you're probably asking, but what is electronegativity? Well, electronegativity is a tendency to attract electrons. So essentially, fluorine, which has the greatest electronegativity of 4, is a lot more likely to attract electrons than any of the other elements. Molecular bonds, on the other hand, form when nonmetals share electrons. For example, in water, or H2O, is made up of oxygen, which has 6 valence electrons, and 2 hydrogen atoms with 1 valence electron each. Oxygen will share 1 of its electrons with each of the hydrogens, so 1 to the first hydrogen and 1 to the second hydrogen. And then each of those hydrogens will share 1 of theirs, or their only valence electron, with the oxygen. The result looks something like this. With a bond between the hydrogens and the oxygens, where those 2 electrons were shared between the 2 of them, and 2 pairs of electrons on the outside of oxygen. Those are the ones that didn't get to be paired. And then molecular bonds can be further broken down into polar covalent bonds and non-polar covalent bonds. Non-polar covalent bonds are when 2 elements equally share their pair of electrons. For example, in methane, or CH4, and as you can see, non-polar covalent bonds typically have an electronegativity difference of 0.4 or less, so very low. Whereas polar covalent bonds are the unequal sharing of electrons and results in a positive and then a negative end, which we call dipoles. And this is what makes them polar. The electronegativity ranges from about 0.5 to 1.7. Again, this is kind of like a rough number. An example would be for ammonia or NH3. As you can see as I draw it, we have a positive charge end and negative charge ends as well. These types of chemical bonds are intramolecular forces, which bind the elements or molecules together, whereas we also have intermolecular forces, which are the forces of attraction between elements and molecules. These include hydrogen bonds, dipole-dipole, and London dispersion forces. Hydrogen bonds are the strongest of the intermolecular forces, and they occur between a hydrogen atom and either nitrogen, oxygen, or fluorine, or NOF. And then we have dipole-dipole, which are attractions between the positive and the negative ends, or dipoles, of a molecule, like we talked about when we talked about the polar covalent molecules. And then we have London dispersion forces, which are the weakest of the intermolecular forces, and they are a temporary attraction between non-polar molecules due to the formation of temporary dipoles, because non-polar molecules don't form dipoles typically, obviously unless in this instance. Intermolecular forces can influence the physical and chemical properties of different molecules, such as their solubility, reactivity, and melting or boiling point. Solubility is how much a substance, or what we call a solute, dissolves into a solvent to make a solution. The solvent would obviously be whatever the substance is being dissolved into. Soluble is the ability to dissolve in a certain solvent, whereas being insoluble means that a substance is unable to dissolve in a solvent. When talking about solubility in regards to inter and intramolecular forces, the rule is like dissolves like. For example, polar molecules are more soluble in polar solvents, and nonpolar molecules are more soluble in nonpolar solvents. Hydrogen bonds will increase the solubility of polar solutes in water. As the strength of the intermolecular forces, which is obviously like our dipoles and stuff like that, increases, so will the boiling point and melting point. Which is why anything with obviously hydrogen bonds is going to have a greater boiling and melting point than something with London dispersions. Or hydrogen fluoride, which is going to form a hydrogen bond, which is why it has a greater boiling point than HCl, because HCl forms dipole-dipole, whereas hydrogen fluoride forms, obviously, hydrogen bonds. And then the greater the bond energy, the less reactive the molecule will be. For example, we're going to talk about table salt again, NaCl. It is the most common ionic molecule, which is why we talk about it a lot. Anyway, the point is, it's barely any reactive. Like, you don't see your salt reacting when you put it in your pasta water. Whereas if you were to put something like SO2, which is a polar covalent molecule, into your pasta water, you would have quite the reaction. This is because there's more bond energy needed to form ionic bonds, like the NaCl, than needed to form covalent bonds, such as in the SO2. Intermolecular forces and polarity also influence how molecule will react with water. Generally, polar molecules, which includes ionic as well, since they are polar, they are hydrophilic, meaning water-loving, whereas nonpolar covalent molecules are hydrophobic, or water-hating, or water-fearing, whatever you want. And this is because of the attraction between the opposite charges between them, which can form hydrogen bonding. Like, as we talked about, nonpolar covalent molecules can form dipole-dipole, so we have the positive and the negative end, and there's attraction between the positive and negative end from one molecule and the positive and negative end from another molecule, and that is what can form the hydrogen bonding. Anyway, that is everything that I have to talk about today, so I really hope this video is helpful for introducing you to biochemistry, and I hope it provided you with the knowledge that you'll need to help with your learning or education or whatever you intend to do with this knowledge. And don't forget to like and subscribe. Thank you, and have a nice day.